In this lecture, we're going to start to look at some actual chemistry, which is really exciting. I mean, I guess NMR, it's all just science, but whatever. But let's get into the first functional group of organic chemistry 2. This is a nice functional group to help us remind ourselves what we were supposed to have gathered from organic chemistry 1, and that's the ether. So an ether is shown generically as an oxygen surrounded by two R groups, where an R group is just a generic carbon atom / group, something where the direct connection to the oxygen atom in this case is a carbon atom. So it could be an atom or a group. An ether, again, is a functional group. So this looks like an alcohol, but it's got two carbons on either side instead of an OH on one side. So if I remind us, we have an alcohol here. And that could be RO with an H. So it looks like an alcohol, but it's called an ether. Some examples of these are diethyl ether. Now, when you name these things as with the ether kind of nomenclature, we have to put a space in between the ether and the previous word. So there's a space here. But this is an diethyl ether because it has two ethyl groups. So an ethyl group is a two carbon group. And then another example would be if we had two benzene rings. This is called diphenyl ether. I'm going to emphasize that space by putting the ether down a line. And that's a nice molecule to be introduced to because it shows us that when we have a benzene ring as a substituent, it's actually called a phenyl group. Okay, and then we have, there's some other ones. We have, this one's called methyl space tert, let me just write it this way, TERT, tert butyl ether. It has a methyl on one side and a tert butyl group on the other side. Okay. So these are ether groups. You can see that we have carbon atoms attached to either side of the oxygen in every case. And when we name these things, I don't have to look ahead in the notes, but I don't think we're going to get too much into IUPAC naming for ethers beyond, maybe pretty simple. It wouldn't be anything too extensive at this point. But we have carbons on either side. Now, let me just point out that if we have on one side a carbonyl directly attached to the group, this is not an ether, this is an ester. So we can cross that out and say not yet. I just want to point that out, that if you put a carbonyl on one side, it's not an ether anymore, it's an ester. That's a different functional groups. Now, when we do name these things, we'll keep it simple. So, well, that's not how you spell simple. I was thinking about methyl as I was writing simple. Okay, so we're going to keep it simple. What we have is an R group with, we have two R groups attached to the oxygen. We'll say R1 space R2 space ether. Or if R1 and R2 are equal, then di R1 space ether. Okay, so we looked at a few examples of that. We can do just a few more. So if we have something like this would be dimethyl space ether. If we have something like this would be ethyl propyl ether. And what I want to notice here is that for the ethyl and the propyl, what you do is you compare the first letter of each group and you say, okay, let's put the alphabetically, we'll kind of list these groups in alphabetical order. So ethyl starting with E comes before propyl, which starts with P. Let's pick another example. Yeah, this is fine. Okay. So on this side, we have, on the left side, excuse me, we have an ethyl group. And on the right side, we have 4-carbon chain. That's a butyl group. And so we would call this then butyl space ethyl ether. I know based on how I have this drawn that the ethyl group is on the left side, but it doesn't go first because E comes after B in the alphabet. Okay. So we're going to kind of try to keep that simple in terms of the naming, but what's a little bit more important is to consider the ether group as a substituent. That's actually pretty important. So more important. Refer to the ether group as a substituent. Okay. Now, what do I mean by that? Okay, so a little bit of a review. Here is the molecule ethyl. What we say is that the OH is, this is a hydroxy group or hydroxyl group. I guess I'm writing these in alphabetical order. So the first one I wrote was a hydroxyl group, but it can also be called a hydroxy group. That's fine. Okay, now I'm using that, I'm bringing that up to help us understand what we call something like, well, let's put an R group on one side and then we'll have a methyl group on the other side. I'm going to write the methyl group as a CH3 just so that we can see it. If we do that, we can circle the OCH3 and we're going to call this not a hydroxy group, but we'll call this an alkoxy group. I don't think people ever say alkoxyl. So it's an alkoxy group, or more specifically, a methoxy group. Okay, so that's sometimes a little bit more important. So we could have we could have methoxy groups. We could have ethoxy groups, propoxy, and even phenoxy, because a benzene ring directly attached, and the benzene ring can't have anything else on it, but a benzene ring attached to something is a phenyl substituent, and if it's part of an ether, we call it a phenoxy group. Okay, so that's sometimes more important. Like it's sometimes important to look at molecules and be like, oh, hey, look at that ethoxy group on the molecule. Okay. So let's now get into some chemistry. That is some transformation of matter. Very exciting. I want to leave enough up here in case you're, so you don't have to pause as often. So let's ask the question, how to synthesize ethers. Okay, so we have ethers. How do we synthesize them? And by synthesize, I mean make in a lab. Now, it turns out that a lot of these reactions that we're going to study are called name reactions. That is, they are named after the person that took credit for first developing them. So I won't get into the politics of why they're named what. It's, if I could just say, it's probably unhealthy that this is what we've decided to do, because not surprisingly, let me just not get too deep into it, but not surprisingly, there are a lot of the people who have been, whose names are attached to these very important chemical transformations, but a lot of the names that are attached to these reactions, the folks that these were named after mostly demonstrate or represent a single gender and ethnic group. Not surprising, I guess, given how things have progressed through the centuries, but definitely not good for our future, right? Our past doesn't have to be our future. Okay, anyway, back to science. So we call this the Williamson ether synthesis. I have no idea who Williamson is, but what they did was an SN2 reaction. This is what I like to do. This is an SN2 reaction with an alkoxide as the nucleophile. That is to say, I like to, as soon as we say the name, I like to immediately remind everybody how this is just, somebody cleverly using organic chemistry that was already known in a different way. So do they need to have their name attached to it? I don't know. Okay, so sorry, I'll get off that. So we have an alkoxide as the nucleophile. This is a nice transformation for us to start with because it reminds us what an SN2 reaction is. So an alkoxide, if you recall, hydroxide is when we have an OH minus, alkoxide is when we have an RO minus, like an alcohol. It's derived from an alcohol. And we also call an alkoxy group an ether substituent. So alkyl is a carbon-based chain. Alkoxide is RO minus. Alkoxy is when that RO is a substituent on a chain. Now the nucleophile is the positive, right? It's positive loving part of the reaction, okay? So this importantly does the attacking because it has the electrons. And electrons, it's hard because protons are what are absorbed in NMR spectroscopy. So everybody loves protons, but electrons, they do the chemistry. I don't know. If I had to pick my favorite subatomic particle, I don't think I could. But this does the attacking and it has the electrons. Okay, so it has the electrons. So that's a little bit of a review from Organic Chemistry 1. Now, what does it attack? So the nucleophile attacks the electrophile. So this attacks the electrophile, and the electrophile has the positive charge. And it gets electrons. It doesn't have that many electrons. It's what we call electron deficient at the outset of a reaction, but engaging in a nucleophile forms a covalent bond and gives it more electrons. Now think for a moment, what is the most common electrophile? I'll take a sip of my tea while you think the most common electrophile in all of nature is the proton, or H+. So most common is H+. Okay, but we don't use H+ that often in when we learn new reactions. We don't worry about the bonds with H+, let me say it that way, when we learn new reactions, because we're trying to make bonds between carbon and something interesting to build up structural complexity. When we use H+ as an electrophile and it gets attacked by a nucleophile, that's simply an acid-base reaction, where the H+ is our fundamental acid. If we don't worry about its source, it's just the acid, and the thing attacking it, engaging it, making a bond to it is the base. Okay, instead we want to look at a typical SN2 reaction. So an SN2 reaction. In an SN2 reaction, the electrophile is carbon with a good leaving group. Now, what we focused on in Organic Chemistry 1 was a haloalkane. So we could have, for example, bromine attached to a chain. That's going to put a delta minus here and a delta positive here. And then if we attack this molecule with an ether, we can form a product. So how does this work? We have a delta minus on the carbon because it's electropositive. Excuse me, a delta plus on the carbon because it's electropositive. A delta minus on the bromine because it's absorbing electrons from the covalent bond, and it's delta negative. The O minus will engage the delta plus and then push off the bromine atom, and that will give rise to a new molecule. This is actually, again, review from Organic Chemistry 1. We've looked at this reaction, maybe not with this exact substrate, but we've definitely looked at oxygen being a nucleophile, carbon with the bromine atom being an electrophile. It may be that the carbon chain was longer or shorter or had rings or whatever, but allowing the oxygen with a negative charge to attack a carbon with a positive charge, that's not anything that we haven't seen before. We may not have thought about it in several years, but doing so allows us to form a new bond. Now, what I want to do is take a second to look at the structure and realize that the new product forms an ether. So the new product is an ether. Okay. And if we want to name this, this would be methyl space propyl ether. Okay. So this is a general introduction to ethers. We looked at the functional group. We looked briefly at how to name these things, and we also thought about the substituents that were involved. What I want to do in the next lecture is to look more in depth at this mechanism and start to think about these things called curly arrows. If you notice, I actually showed the movement and the flow of electrons. If that's not familiar with to you, don't worry about pausing, rewinding, or going all the way back to your organic chemistry 1 notes. Let's continue on with this discussion, but we'll do it in a separate lecture as we look at the mechanism for the Williamson ether synthesis, okay?